higher. Now, isn't that a board that just screams out cool stuff? That is just cool, okay? A lot of mathematics in there, but just how cool is it? I really do love this topic, okay? Differential equations. It's all about rates of change. Why is it so important? Because if you think about it, change is everywhere. It's part of life. It's a natural part of life. Everything is changing. Nothing is constant, okay? As time goes on, things change, okay? People speed up or slow down in their cars or on their bikes, okay? Weather changes from day to day, from minute to minute, from hour to hour, okay? Your rate of learning changes, okay? Even the tea that you are drinking is a little bit cooler now than it was a minute ago, okay? Things are always changing, okay? And on the board is just some examples of some really cool things that are changing, okay? What this video is about, it's about rates of change and differential equations, okay? Stay tuned because I can try and make it as enjoyable as possible, but come on, it's calculus, it's calculus. You don't need to jazz this up. It's already pretty cool and important on its own, okay? Well, I'm hoping that you like this video about differential equations. So I'm going to begin with rates of change itself, okay? On the board, you've got 4 different graphs illustrating rates of change. You've got one variable changing in relation to the other. So look at this graph here. We've got x and y, and we've got a straight line. If you look at the 2 points, it looks like it's set up to find the gradient between 2 points, isn't it? Well, a gradient is a rate of change. It's a rate of change of y with respect to x, and that's why we call it dy dx. dy dx stands for the rate of change of y with respect to x. You might think of it as changing y values over changing x values, but it's really about how y is changing as x changes. As the x-coordinate changes, how does the y-coordinate change? That's what we mean by gradient, the steepness of a line, okay? And well, it is dy dx, okay? But these other ones, they're not necessarily going to be expressed as dy dx. They might be expressed as some other derivative expression, okay? Let's look at this one here. This is dp dt. Any ideas what the dp and dt actually means? Well, quite often we're measuring a rate of change with respect to time, okay? And the horizontal scale is supposed to represent time in years, and the vertical scale is supposed to represent population. This could be a population graph showing you the rate of change of population. That rate of change is written as dp dt. It literally means the rate of change of population with respect to time. How population changes with respect to time, okay? Let's look at this one here. A derivative expression for this could be dv dt. What does the dv dt means? Well, again, using time as the horizontal scale, it's how the volume of something changes with respect to time. You can't see it because it's a bit small, but it's labelled volume of gas produced, okay? Could be the volume of air that's in a particular room at a given moment, okay? And the air has been sucked out of the room. We've got more air being pumped into the room. Or you've got someone blowing up a balloon, okay? Or someone actually blowing up a football, all right? So you've got the rate of change of the volume with respect to time. And obviously you can have other graphs, rate of change of surface area with respect to time, rate of change of area, rate of change of length with respect to time. All these things are changing with respect to time. This one here, this is temperature and time, okay? Now what letters will we use here? We used y and x because of the way the axes are labelled. We used P for population, used V for volume, maybe capital A for area. What about this? Temperature. No, we don't generally use T. We tend to use theta for this, the Greek letter theta. It's just so we don't confuse ourselves with too many T's, really, to be honest. Okay, so d theta to T, that is representing the rate of change of temperature over time. A good example here is cups of tea, because I do like tea, to be honest. Okay, some people are coffee drinkers, not me. I like tea. Okay, and obviously you start it off with a boiling water in a kettle. Okay, and of course over time, then the temperature is going to decrease. Okay. And this is a rate of change of temperature with respect to time. The importance of these are that you need to associate rates of change with derivative expressions. That is a really important point. Okay? You need to know what is changing with respect to what. Is a volume changing over time? Is a population changing over time? Is a variable y changing with respect to x? Because once you know what is changing, then you can set up a derivative expression. And that is our basis, our starting point for differential equations. Okay? Now let's have an example involving rates of change in what could potentially look like a complicated question. what you need to be able to do is you need to interpret exactly what the question means. Okay, so let's just read it out. Given that the area of a circle a centimetres squared is related to its radius r centimetres by the formula area equals pi r squared, so I'm going to stop there. All this is saying is, look, here's a reminder, area of a circle is pi r squared. Okay, so when I say you need to interpret the question, pick out the important bits of what it's saying to you. So the first bit is saying, look, area is pi r squared, and we're going to do something with that. And that the rate of change of its radius in centimetres per second is given by dr dt equals 5. Let's talk about what that means, okay? dr dt. Okay? dr dt is a derivative expression for the rate of change of r with respect to t. In this case, it's saying the rate of change of the radius, okay, with respect to time. And it's saying that dr dt is equal to 5. What's the units bits for? Well, because if it's changing, okay, the radius is changing, and it's measured in centimetres, and it's changing over time, so it's centimetres per second, hence centimetres per second, okay? So what I've done is I've just interpreted that bit for you, all right? So in terms of what this is saying to you, I've interpreted everything up to there for you, okay? We need to find dA dt when r equals 3. So we need to find dA dt when r equals 3. So I'm going to put dA dt equals, and then question mark. Right. Now how do we do that? Well, we know dr dt, and for some reason we've been reminded about this expression for the area, so we must use that somewhere. Now let's just think about this. This is about rates of change, which is about derivatives. Why not differentiate that? And just see what happens for a moment, okay? Why not differentiate that, okay? So when we differentiate that, we're finding dA dr. This is where you've got to be really clear about which letters you're using. A is this in terms of r, so as a derivative rate of change, it's how area changes with respect to the radius, dA dr. Differentiate that. The pi is a number, just a constant value, so differentiate r squared, you get 2r. So you get 2 times pi times r. That in itself is a fascinating result. Okay? You start off with the area, you differentiate it, you get an expression for the circumference of the circle. Wow. Not a coincidence, but I'm not here to go on about that. Okay? I just thought I'd throw that out there. Okay? So we've got the edit. So what are we going to do with this? Now, I'm going to ask you to think about this. Is there a way, using your knowledge of derivatives, to get an expression for dA dt using dA dr and dr dt? Yes, there is a way. It's called the chain rule. Remember the chain rule? Okay, let me just write it out, okay? If we have dA dr multiplied by dr dt, that is effectively the chain rule. You might have remembered it as dy dx equals, say, dy du times du dx. Okay? We can use these letters as well. Remember the dt's, so the dr's would cancel, just left with dA dt. Okay? So what we're going to do is just multiply these together. So dA dr is 2 pi r, and dr dt is 5. So 5 times 2 pi r, that's 10 pi r. So now we've got an expression for dA dt. And the question says, find dA dt when r equals 3. So what we do is we substitute r equals 3, and we've got dA dt is equal to 10 times pi times 3. I'm going to leave it as 30 pi. I'm going to leave it as an exact answer. You can write it as a decimal if you want. I'm going to leave it as an exact answer. Okay? This is only a little add-on because I just can't resist these things. Remember I pointed out how I was so fascinated with this, start with the area of the circle, differentiate to get the circumference. Well, let's just look at it with the volume of a sphere. Remember, volume is 4/3 pi r cubed. What happens when you differentiate that, when you find dV dr? Well, the 3 multiplied by 4/3, it's just going to be 4. The pi is a constant, stays in it, and then you've got r squared. The surface area of a sphere, yeah? How fascinating is that? Differentiate this volume, you get the surface. Again, that's not a coincidence, okay? That's just one of those really cool, interesting mathematical facts, okay? Not really related with what I'm talking about, but I just thought I'd throw it out there. I like throwing out these mathematical facts because it makes people think, oh, wow, yeah, really exciting. That's what maths is, isn't it? It's excitement everywhere. Anyway, I must get on with the rest of the video. Right, let's do another rates of change question, shall we? So in this question, the volume of a hemisphere V, cubic centimetres, is related to its radius r centimetres by the formula V equals 2/3 pi r cubed. And the total surface area S square centimetres is given by the formula S equals pi r squared plus 2 pi r squared equals 3 pi r squared. Just take a moment to think about that. Now you need to know what these shapes are. So I've just put that in there for you. You don't need reminding, of course, but you need to know what these shapes are. That's a hemisphere, it is half a sphere. And the formula are normally related by the radius. So I don't know if you can see that, but there's a line there representing the radius. Okay, so circle on top and then curved surface underneath. Okay. Now the volume is given by 2/3 pi r cubed, because a volume of a sphere is 4/3 pi r cubed. You do need to know that. Okay. The surface area of a sphere, why is it given to us like this? It's just basically to help you to understand where it's actually come from. So the surface area includes the bit at the top, which is flat, and the flat bit is just a circle with radius r. So the circular bit is just that bit, pi r squared. In terms of the curved bit, the curved surface area of a sphere, a total sphere, is 4 pi r squared. So this bit here, half of it, is going to be 2 pi r squared. And so when you put the two together, you get 3 pi r squared. So that's why the surface area is 3 pi r squared. I just thought I'd give you some explanation there. So that's really the first part. Okay, essentially it's not telling you anything new, is it? It's basically saying, look, you're going to have to use these for the question we're going to ask you to do. Okay, that's really what it's there for. It's saying you're going to have to use these formulae for what is coming up next. So what's coming up next? Given that the rate of increase of volume in cubic centimetres per second, dV dt equals 6, find the rate of increase of surface area ds dt. Okay. Let's just write these things down. So it says dV dt equals 6. So look, what I've done is I've just written down all the important parts of the question. Okay, we're told this, this and this. Okay, that's what we're told. dV dt of course means rate of change of volume over time. And that's why it says, given the rate of increase of volume in cubic centimetres per second. Remember, volume cubic centimetres, time seconds, hence cubic centimetres per second. And it's 6, okay? What does that actually mean, okay? What it means is that after each second, the volume increases by 6 cubic centimetres. That's what it means, okay? So after 1 second, volume's increased by 6. After another second, another 6. That's what dV dt actually means, okay? We need to find the rate of increase of surface area. So we need to find ds dt. Okay, that's our goal. Again, we're going to use the chain rule to do it. Okay, we use the chain rule to do it. So that'll feature somewhere, and it's a good idea to differentiate these just to see what that gives us. So what I'm going to do is I'm just going to make some space. I'm going to get rid of that and that. Okay. One of the reasons I like working on this board, it's more adaptable, it's more versatile. I can actually do these things more quickly. Okay, right, let's look at differentiating these. So dV dr, because it's differentiating v with respect to r, so 3 times 2/3 is going to be 2, so that's going to be 2 pi r squared. Okay, remember I talked about that in terms of differentiate the volume, get the surface area. That was the surface area of the hemisphere, of course, 2 pi r squared. ds dr is equal to, it's going to be 6 pi r, and we're going to have to use those to find ds dt, aren't we? Just think about it for a moment. How to use the chain rule to get ds dt? Well, look, what we need to do is we need to have an expression with the ds on top. Yeah, we need to have a ds on top. Which of these is that going to be? So that one there, isn't it? ds dr. Okay. We also need to have an expression with a dt on the bottom. So we're going to have to multiply it somehow with something dt. Which of those is it? It's that one there, isn't it? So we have to multiply by dv dt. Okay. However, look, if you notice, that's giving us too much. You've got ds, dv, dr. There's nothing cancelling. Okay. We want the ds and the dt. So what we need is something that will make the drs cancel. So you want a dr on the top, and something that will make the dv's cancel. So you want a dv on the bottom. Is there an expression that will allow us to use that? Well, we've got this there, dv dr. If we take the reciprocal of that, then it's fine. Okay, and that's what we're looking for. So ds dr, let's put that in, is 6 pi r. and then dv dt, that is multiplied by 6, and then dr dv is the reciprocal of that, so it's over 2 pi r squared. Okay? So I can simplify on it, so 6 times 6, 36 divided by 2, that's 18. And then the pi's are going to cancel, and then r over r squared, so 18 over r. Okay, and that is it. And that's our expression for ds dt. What does that mean? How do you interpret that? It's the rate of change of the surface area over time. In other words, as the volume is increasing at a rate of 6 cubic centimetres per second, then the surface area is also going to increase. It's increasing because it's positive, more on that later by the way. It's going to increase at this rate. So you substitute r equals whatever in, and it gives you the rate of increase. Obviously, it's dependent on the radius, okay, of this hemisphere, because that affects the surface area, doesn't it? Now we'll get on to my favourite bit, which is talking about the differential equations themselves, okay, the differential equations themselves. Well, I've shown you this board already. Absolutely love this board, by the way. These here are examples of differential equations. Okay? What makes it a differential equation? Quite simply, it's got a derivative expression in it, d2y dx squared, or dy dx, or d theta dt, or dy dx, again dy dx here, and it's got an equals. So these are all equations because they've got an equals, hence it's a differential equation. That's all you need to know about what a differential equation is. Now there are different types of differential equations. Okay, you've got first order differential equations, so that will be this one there. That's a first order differential equation. That one there is a first order differential equation. That one there is a first order differential equation, but that one isn't. That one's a second order differential equation. Now probably you can guess what we mean by a second order differential equation. Yes, a second order differential equation has got a second derivative, d2y dx squared. Okay, if it's only got a first derivative, dy dx, then it's a first order differential equation. That's only got a first derivative, hence a first order differential equation. Same with that. Okay, so anything that's got a first derivative only, it's a first order differential equation. If we had a d3y dx cubed term in there, that would be a third order, and obviously then you have an nth order differential equation as well. Okay. You can't quite see that, but that's supposed to be some sort of integral. More on that later on, okay? We're not talking about integration just yet. Just want to show you this, okay? Because what I've done is I've just got rid of the pictures, okay? In terms of, depending on what course, if you just look at the standard A-level mathematics, okay, then you don't actually need to do that one. That's further mathematics, okay? Solving the second order differential equation or dealing with them. In just A-level mathematics, you might look at something like this or something like this, okay? This is a first order only, but in terms of what you need to do, you're only going to be interested, let's just put, oh, I can't, let's just cross that one out. Oh, don't need to see that, no. We're just looking at these types of differential equations. So what I'm saying is, in A-level mathematics, the simplest differential equations you'll meet are when it's dy dx equals something, or d theta dt, or dA dt, or dv dt, or dv dr equals something. Basically, you've got a derivative equals something. Okay, the more challenging ones, okay, like these ones there, okay, that's for further maths only. Okay. Now, you need to know how to set up your own differential equation. Sometimes that can be the difficult bit. Okay, so I'll give you a couple of simple examples just to get you going. This is setting up a differential equation. Okay, so here it says in the decay of radioactive particles, the rate at which particles decay is proportional to the number of particles remaining. Write down an equation for the rate of change of the number of particles. Looks like a really complicated question, doesn't it? Okay. However, there's no work required, you just got to be able to write down your answer. So let's just see what we need to do. We need to find an equation for the rate of change of the number of particles. This graph is kind of designed to try and help you really, okay? So we've got number of particles, that's labelled capital N. You can go for P for particles if you want, but capital N for the generic number, okay? And it's measured over time, okay? Because when you talk about the rate at which particles decay, we are talking about the rate over time. That is implied in the word in the question. You've got to know the implication that these particles are changing over time. Okay? So can you think of a derivative expression involving the rate of change of the number of particles n over time, it's just going to be this, isn't it? dn dt. Okay, so that stands for the rate of change of the number of particles with respect to time, dn dt. Okay, for an equation, you need dn dt equals. You need dn dt equals something. Let's read the question again and see what it is. It says it is, now the word is there is essentially equals, okay, proportional to the number of particles remaining. It's proportional to the number of particles remaining. Let's think about what we mean by proportional. Okay, when we say y is proportional to x, then that's what we normally write down, the proportionality symbol, y is proportional to x. Then we write down an equation connecting y and x. It is y equals kx. Okay? Remember, directly proportional means as one increases, so does the other at the same rate. Okay? If y was proportional to x squared, we'd write this. If y is proportional to the square root of x, then the equation connecting y and the square root of x would be this. Now in this one, it's proportional to the number of particles. Okay. Now we've got the letter n to represent the number of particles, so your relationship between the number of particles and this being proportional to the number of particles has got to be kn. That is it. Just as this here would be k times x squared, or k times... Basically, when it's proportional, it's k times the thing it's proportional to. Okay. The next thing you've got to consider is this. Is it increasing or decreasing? Now, the graph shows you it's decreasing, of course, over time, but also there's the word decay in the wording there. Let's just check all the others again. No, it's just that one there. There was the word decay, which is decreasing. So what that means is it's going to be negative. So your final equation is going to be dn dt, the rate of change of n with respect to time, is equal to negative kn. The negative is important because it means it's decreasing. Okay, I'm hoping you understood that. There's another example for you coming up now. Here it is. A population is growing at a rate which is proportional to the size of the population at a given time. Write down an equation for the rate of growth of the population. The graph is there to help you. Okay, so what we'll use is the letter P to represent the population, and of course T for time. Okay, can you think of a derivative expression for the rate of growth of the population? Essentially, the rate of population change over time. It's dp dt, isn't it? dp dt. I want an equation, so dp dt is equal to something. Let's have a look. It's proportional to the size of the population. So it's going to be k times by p, proportion. And next thing, is it a growth? Yes, it is. It's an increase, okay? It says there it's growing, it says there it's a growth, and the chart shows you that it's generally increasing as well. So the importance of that is that the k is positive. dp dt equals kp, okay? I'm hoping you found those examples helpful. Hi, you okay? I do love this picture. Isaac Newton, one of my all-time favourite mathematicians, okay? Not my favourite of all time, but one of them, okay? Did a lot of great work, of course. So this is just a, a blatant opportunity to just talk to you a bit about Newton, okay? So some people have interpreted that quote differently over the years, okay? I guess it's impossible now to know exactly what the quote is supposed to mean. The way I like to look at it is that Newton is crediting all the mathematicians, the great mathematicians that went before him. Okay, mathematicians like René Descartes, who saw the relationship between geometry and algebra, and hence coordinate geometry was born. The use of graphs was helpful with Newton's work in calculus, of course. I like to look at it as paying homage to those mathematicians that went before him and saying, look, I'm just building upon the great works of these mathematicians that have gone before me. Okay, that's the way I like to look at it. I try to keep a positive spin on things. Okay, if it meant something different, fine, but that's kind of the way I look at it. Okay. So why am I just sipping my tea here as I'm talking to you? Okay. Well, obviously it's related to the next example I'm going to give you, which is this. I can find it. Ta-da! There we go. It's about Newton's law of cooling. Okay, hence my cup of tea. Okay. Now, as I keep on mentioning in various videos whenever I get the chance, okay, You make a cup of tea, use boiling water, of course, okay, 100 degrees, okay, otherwise it's not going to brew properly, is it? Okay, I was looking for the right word there. And then it cools down, okay, and this graph here, there it is, just shows you a little bit about the rate of cooling on that. So it's going to cool down, okay, so for example, you've got the maximum temperature which it's started, okay, and then it cools down rapidly, and then it sort of tails off, because there's a big difference between the actual temperature of the tea and the room temperature, okay. This example here gives you the room temperature, okay. In a room like I'm in now, maybe about 20 degrees, maybe a bit over 21. Now, probably at 20 degrees, I'd say, okay. But if it was outside, you know, it's January at the moment, actually no, it's February, I forget the date, I'd say it's about 7 degrees outside. Anyway, there's a big gap, isn't there, between the actual temperature of the tea when it's first made, and so there's a big decrease straight away. The tea is trying to acclimatise as quickly as possible to its surroundings, okay? You know what it's like a human thing, isn't it, okay? When you get into a new room for the first time, you take a while to acclimatise. You're taking everything in very quickly, and then suddenly things just sort of slow down a little bit more. You take the time a bit more, then you just pick up these little things. Anyway, what I'm saying is effectively the same is happening with the temperature. It just gradually gets closer and closer, and then eventually it'll get to room temperature, won't it, okay? Anyway, Newton came up with his law of cooling. Let's just talk about that for a moment, okay? What do you suppose would be a correct differential equation, which is Newton's law of cooling? Well, it states that the rate of loss of temperature of a body is proportional to the excess temperature of the body over its surroundings. Write an equation expressing this law. A differential expression for the rate of change of temperature, if you use theta for temperature, t for time, d theta dt is equal to. And now it's cooling, so it's decreasing, so it's going to be equal to negative something. It is proportional to, so it's going to be equal to negative k times something. And then we just need an expression for the excess temperature of the body over its surroundings. So if you look at theta as being the actual temperature, that is changing, and then theta 0, sometimes we use theta 0 for room temperature, okay, the surrounding temperature. It will be the difference between the two, hence theta minus theta 0, okay. Known as Newton's law of cooling. It's also used by doctors to estimate the time of death. Isn't that a fascinating fact? I think it's fascinating, okay. Whenever you see one of those old, oh, here comes the bell. Whenever you see one of those old murder style things, okay, from the 1970s, 80s or whatever, okay, I like to think of the medical examiner that's in the corner of the shot, not quite out of shot, because you know he's got to be doing something. It's going to help the police officer in charge of investigating the murder. I like to think that they're working through their differential equations and they're trying to work out the precise time of death. Okay, yeah, that sort of thing goes on. No, these days you can use computers to do it. Okay? It takes the fun out of all the work that the doctors have to do. But yeah, it's got an important application there. Okay, well, I'm gonna finish my tea because I made this for a reason, but I don't want it to get cold, okay? So I'll finish this off and then I'll do some more examples for you. I'll see you soon. Amazing, it's already got a bit cooler now in the last few minutes I've been speaking to you. Hi, this is Jonald. Jonald is a snowman, lovingly built by some further math students 2 years ago, okay? When it was snowing one day and they decided to build a snowman. Under my instruction, I might add, because it tied in nicely with the next example I'm about to show you, okay? I just wanted to give a reminder about Donald, okay? I'll turn the lights on, okay, for the example. Maybe just take time to read through it first as I get the lights. You read through that, okay then? The head of a snowman, hence the building of the snowman, you see, okay? And then we just had a look to see how long it took the snowman to melt away. The head of a snowman, a radius r centimetres, loses volume by evaporation, okay? At a rate proportional to its surface area. Kind of makes sense, doesn't it? The volume it's lost is a rate proportional to its surface area. Because it's the surface contact that is in contact with the outside air, that's surroundings, that is affecting its shape, isn't it? It's going to melt, and it's going to get smaller because of the surface that is constantly evaporating, okay, when the outside temperature is greater than the temperature of the ice itself and the snow that's made from. Assuming that the head is spherical, difficult to do that, isn't it, to get a perfectly spherical snowman. Assuming the head is spherical, the volume of a sphere is 4/3 pi r cubed, okay? And that the surface area is 4 pi r squared. So this bit doesn't tell you anything new. It's basically saying, look, these are probably going to be helpful for this example. Write down a differential equation for the rate of change of radius of the snowman's head. I do love this example. It's about snowman and snow. Hey, who does not like snowman and snow? And it's also got a lot of mathematics in there as well. Okay? Maybe one day I should get my class to build a snowman of some mathematical figure. Okay? Newton, of course, because of differential equations and so on. Okay? Anyway, let's have a look at this. So, what does this bit here mean? The head of a snowman of radius r centimetres loses volume by evaporation at a rate proportional to its surface area. We've got to write something down from that. We've got to write down a mathematical statement about what it's saying. Okay, so if a snowman of radius r loses volume, it loses volume over time, doesn't it? Yeah, it loses volume over time. So this is saying dv dt. It's another way of saying the rate of change of volume over time. Okay, so the volume is decreasing at a rate proportional to its surface area. So dv dt equals, and it is decreasing, so it's negative, proportional to, so k multiplied by the surface area. I'm just going to go with capital A for the moment. So that is what the first sentence says. dv dt equals negative ka. Replay the video again if you didn't quite understand it, because it's really a rather important point. Okay. We're told what the surface area is. We'll probably come back to that. We're also given this. The volume of a sphere is 4/3 pi r cubed. Okay. So V equals 4/3 pi r cubed. As I said, we'll come back to the surface area probably. What do we need to do? Write down a differential equation for the rate of change of the radius of the snowman's head. So what are we trying to do? Rate of change of radius means how r changes over time, because that's how the radius is changing over time. So it's dr dt, and it's capital R this time for the radius. So dr dt equals, that is what we need to find, dr dt. And as soon as you set it up that way, you can go ahead and start to answer the question. Chain rule is often used. Okay, so let's just get rid of this. Dr dt. We've already got dv dt, so let's write that down. We've got dv dt. So having the dt on the denominator is good, but we need a dr on the numerator. Okay, so if we're using the chain rule, we're going to have to get a dr on the numerator, and the dv's are going to have to cancel. So we need to have dr dv, don't we? If we can get dr dv, then we've done it. Go back to this. We can differentiate that and use dv dr, can't we? Okay. Maybe I should have used a capital letter r there. Let's just change that to a capital. Okay. I'm so used to using lowercase r for the formula. Let's differentiate that then. So dv dr. I must have done this a couple of times now already in this video segment. 3 times 4/3 is 4, so it's 4 pi r squared. So dv dr is 4 pi r squared. Okay. Or if you want, it's just A, the surface area. Okay. Remember, I used the value letter A there to represent 4 pi r squared. So you've got dv dt, which is negative ka, negative k times by A, times by dr dv, the reciprocal of that, don't forget. So it's going to be over 4 pi r squared, which is just capital A. And there we go. The A's will cancel, and it's just negative k. So dr dt equals negative k. What does that tell you? The fact that dr dt equals negative k. Remember, k is a constant, means it's a constant decrease, doesn't it? Okay, it's not actually dependent on a variable such as r, it's a constant variable. Okay, dr dt is equal to negative k. Okay. I'm hoping you enjoyed that example. Yeah, it's snowman. I do love that one. I do love that example. Okay, just a pity I didn't get a chance to do it in the classroom this year. At least I got to do it in the video, and you can watch it as many times as you like. Okay. All right. I'll see you again. No, I think we need to have one more. Yes. let's leave it on the John Old notes, because I do love John Old. Okay, there we go. Just enjoy John Old. Well, there you go. There you go. I hope you enjoyed this section of videos about differential equations. Okay, hope it's enlightened you, and I really hope you've got a better sense of why mathematics is just so important in the real world. Remember, everything is changing. Okay, just think about the weather, for goodness sake. It's just one thing, the weather, constantly changing. All right, and various other things as well. Okay, but anyway, hope you enjoyed it. And remember, always love mathematics, particularly do love calculus. Yes, calculus is the best. I'll see you again.